All right, let's just jump right in. We're not just going to talk about data or information today. Nope. We're going way deeper. We're going on a journey into the meaning of, well, meaning itself. What is it, really? Where does it even come from? And what if I told you the answer has been hiding in plain sight, in a totally different field of science? So, this all kind of starts with a guy named Claude Shannon. Back in 1948, he basically invented the digital age with one paper. He gave us the bit, this perfect way to measure and send information. It's thanks to him you can send a message halfway around the world and it gets there perfectly. But Shannon's theory had this giant gaping hole in it. It could tell you how to send the message, flawlessly, but it had zero clue what that message actually meant. To his theory, a beautiful line of poetry and a string of total nonsense were exactly the same, as long as they took up the same number of bits.
And that leaves us with this huge mystery, right? If the meaning isn't actually baked into the bits and bytes of the message itself, then where in the world is it? That's the big puzzle we're going to try and solve right now.
To find the answer, we have to do something a little weird. We're going to leave computer science behind and jump into the world of early 20th century physics. We need to talk about one of the most incredible mathematical minds you've probably never heard of, Emmy Noether. And it turns out she stumbled upon a principle so deep, so fundamental, it might just be the key to this whole thing.
The key idea she worked with was something called symmetry. Now, when you hear symmetry, you probably think of, I don't know, a butterfly's wings, right? A perfect reflection. But in physics, it's a much bigger idea. A symmetry is any property of a system that stays the same, that remains invariant, even when you change the system, when you transform it somehow.
And here's where it gets amazing. Noether's theorem revealed this unbelievable connection woven into the fabric of the universe. She proved that for every continuous symmetry you can find in nature, like the fact that the laws of physics work the same here as they do on the other side of the galaxy, there's a corresponding physical thing that has to be conserved. In that case, it's momentum. It's like symmetry and conservation are two sides of the very same coin.
Okay, so this is where it all comes together. This is the grand hypothesis. What if this incredible principle from physics doesn't just apply to, particles and energy? What if it applies to information, to knowledge? What if meaning itself is one of these conserved quantities, born out of a kind of symmetry?
Okay, so how could this possibly work? Let's make it super simple. Look at this. It's a triangle. Easy enough, right? Your brain sees this and instantly gets the concept, the schema of triangle. Now, let's transform it. We'll rotate it, maybe shrink it, move it over here. The raw data, the position of the pixels on your screen, has completely changed. But what is it? Yup, it is still a triangle. The core idea, the fundamental concept, hasn't changed at all.
And that, right there, is the whole secret. The meaning isn't its position or its color. The meaning is the triangleness of it. The meaning is the one thing that remained constant, the thing that was invariant across all those transformations. It's the conserved quantity.
And this idea, it actually has a name. It's called Noetherian semantics, and it's a totally radical way of thinking. It says that meaning is not a property of the data, not the pixels, not the bits. It's a property of the data's symmetries. You find meaning by figuring out what stays the same when everything else is changing.
So you can see how different this is from Shannon's old way of thinking. Shannon's information is all about the data itself, the specific message. It's fragile. You flip one bit and the whole message is different. But Noetherian meaning, that's all about the invariant, the deep structure. It's robust. You can change all kinds of things about that triangle, but as long as that core triangleness is conserved, the meaning is still there.
I mean, this is a beautiful theory, right? It's so elegant, but it immediately leads to a very big, very practical question. How in the world do you teach a machine to think like this? How do you get an AI to stop just memorizing data and start searching for these hidden, unchanging symmetries? Well, for a hint, we can look at, of all things, how children learn. Let's bring in another genius, the developmental psychologist Jean Piaget. He argued that kids don't just soak up facts like a sponge. They build these little mental models of the world. He called them schema. A child builds a schema for doggy, 4 legs, has fur, barks, and that model helps them recognize all the different dogs they meet.
And what's just wild is that a major type of machine learning algorithm does the exact same thing. It runs in this constant two-step loop. First, there's the expectation step, where it tries to fit new data into its current models, its schemas. That's just like a kid assimilating. Then comes the maximization step, where it tweaks its models to better explain the data it just saw. That's accommodation. The AI is literally learning like a child, building and refining its understanding of the world by trying to find the best, most stable patterns.
So we have a theory of meaning as invariance, and we have a plausible way an AI could learn it by acting like a developing child. It all lines up so nicely. But was there any proof? Did this actually work in the real world? Well, the answer came from the last place anyone would have looked. Not some huge AI lab, but a student's master's thesis. Back in 2012, a student named Ilkka Kosonen was tackling a very specific problem. He was trying to make sense of all this messy, noisy physiological data, heart rate, skin sweat, coming from people playing video games. He wasn't trying to solve the riddle of meaning. He was just trying to analyze his data. But here's the thing about the method he used. Instead of him telling the computer what patterns to look for, his algorithm went hunting on its own. It automatically searched for the simplest possible set of core patterns, these prototypical response curves that could explain all that chaotic data. In other words, without knowing it, his program was looking for the invariant schemas hidden in the noise. It was looking for meaning.
And get this, it worked. It worked insanely well. The system got so good at recognizing these core, meaningful patterns that it could look at a player's raw biometric data and tell you what was happening in the game, like the difference between when a player died and when a new round started, with nearly 90% accuracy. It was literally finding the meaning in the signals.
He had done it. Completely by accident, Kosonen had built a working system that did exactly what the theory of Noetherian semantics predicted. It learned meaning by ignoring the noisy surface-level data and instead discovering the deep underlying schemas that were conserved from person to person. It was an accidental blueprint for a machine that could actually understand.
So where does this leave us? If this theory holds up, it could completely change how we think about building intelligent machines.
So let's just recap the big ideas to take away from all this. Number one, meaning isn't in the data. It's in the symmetries, the stuff that doesn't change, which leads to number two. Real understanding isn't about memorizing facts, it's about discovering those invariant things. And we've seen that AIs can learn to do this using methods that look a lot like how kids learn. And maybe the biggest takeaway of all is that the path to true AI might not be about building bigger and bigger models. It might be about finding the right principles.
And really, it all boils down to this one powerful thought. When we're looking for patterns, for constants in a world of change, for the deep structures underneath all the noise, we're doing more than just analyzing data. In a very, very real sense, the search for symmetry is the search for understanding itself. And that leaves us with one final, kind of mind-bending question to chew on. If finding meaning is all about finding symmetry, and understanding is just the act of seeing it, what fundamental symmetries about our world, about our own minds, maybe about the universe, are we still completely blind to? What new worlds of meaning are just sitting there waiting for us to see them?